is employ state space average modeling for the modeling part. Why? The reason is simple, because it's the simplest thing to do. Why should we go for the much complex, say, method or say trajectory sensitivity approach, which was proposed by IIEST, or for say discrete time approach, or why should we bother to construct maps at all? The reason is very simple. You see, when it comes to modeling approach, the state space average modeling can only predict the onset of flow scale instability or Hop bifurcation or flow time scale instability, which basically manifests as kind of a slow moving oscillation cycle, right? So say you are dealing with a DC-DC buck converter which is operating at 10 kilohertz or 20 kilohertz. What will happen is that often you will see kind of a slowly rolling type of wave which has been impressed upon the DC component. And you will see that the frequency component often manifests as say 500, 700 or up to 1000 hertz. Then we can say that the slow scale instability has manifested, which can only be predicted by state space average modeling. But that is the basic part of it. Now let us delve something deeper and let us begin for starting. Let us just consider the case of the DC to AC voltage mode controlled inverter. Now, there are various ways to look into a power electronic converter, right? But we are going to take the approach of a scientist, not necessarily that of an engineer, at least for the time being. And we are going to see how, at least from the theory of dynamics, how is the system, how the system is like, how the voltage mode control inverter, at least for this case, we are considering a single phase inverter, because you see, when we are dealing with basically the part of dynamics, it is not wise to go for the three-phase inverter because it will only make the calculation more cumbersome, but the manifestation of various types of instabilities will be the same, whether it is in a three-phase system or a single-phase system. So we are not going to bother about the three-phase system at this moment. But I should stress at this point that whatever dynamics that we are going to encounter for the single-phase case will inevitably manifest for the three-phase case also. Now, the voltage mode for inverter, if you just take a look at its transfer function, you will see that the transfer function is highly similar to that of a DC-DC buck converter. Sorry. Only the thing is that the magnitude of it basically gets doubled for the power stage. Why? Because you will see that the voltage mode controlled inverter, at least for the single phase case, since we are talking about it, it will inevitably act in a buck mode. It will basically inevitably step down the voltage just like the buck converter also. So, from a qualitative
yes. Publish అవ్వాల్సింది ఉంటే మనం సబ్మిట్ చేసింది ఏముంది ఒక వర్డ్ డాక్యుమెంట్ లో పెట్టాం కదా మొత్తం పేరు తీరని పేసి
Yes, sorry, was that a question? I couldn't get you.
Yeah, okay, you please carry on. Okay, I have muted that.
Okay. Thank you. The thing is that the system is a non-autonomous system. Okay. Now, what does it mean by autonomous or non-autonomous system? And this is a very important part, and this is a very important thing about the theory of dynamics, I would say. See, autonomous means when there are no external frequencies being imposed upon the system. And non-autonomous means there is an external forcing function, or there is some, at least one forcing frequency that is being impressed upon the system. So what does it mean? It means that when it comes to the voltage mode controlled inverter, you are very much familiar with the pulse width modulation, with the basic fundamental theories of pulse width modulation schemes. You will see that there will be a carrier waveform and there will be a modulating waveform. And what will happen is that through the modulating waveform, basically we set the frequency of the system. That is why it is called a forcing function. Now, in case of the DC to DC converter, you will see that only the switching frequency is being impressed upon the converter to the controller, of course, and there is only one forcing function, which is basically the switching frequency. In addition to that, in case of the DC to AC inverter, there is also another forcing function, which is the 50 Hz or 60 Hz, which basically comes through the reference waveform. So we can now safely say from a dynamical perspective, inverters have two forcing functions, reference waveform of 50 or 60 Hz and switching waveform of kilohertz or even megahertz range in these days due to implementation of gallium nitride devices. And one interesting thing is that when we are basically analyzing stability of power electronic converters, what we do? You see, we often basically analyze the stability of a fixed point. And that is the case if we construct a map. And in the vicinity of the equilibrium point, we basically analyze the stability of the fixed point. But especially in systems like, I think in overall power electronic converters, in case of power electronic converters, it would be much more prudent if we just opt for analyzing stability of periodic orbits. Why? Because when we are analyzing stability of periodic orbits, we will see that it basically not only goes through say for the case of the buck converter, the periodic orbit goes through two linear time invariant subsystems. Why? Because if you can just remember, in case of the through the pulse width modulation scheme, you will see that there are two switching. Okay. Now, where those two switching will occur depends on what is the exact nature of the pulse width modulation scheme. I mean, is it a leading edge scheme? Is it a trailing edge scheme? Or is it a double edge modulation scheme? If it is a case of the leading edge or trailing edge modulation scheme, what will happen is that there will be one forced switching where there is a discontinuity which basically comes to the modulating waveform. In the modulating waveform, you will see that especially if it is a sawtooth type of waveform, then it will be either leading edge or trailing edge. So there will be a forced switching in case of the discontinuity, and in addition to that, there will be also we basically term it as kind of a state event switching. When basically what will happen is that you see that the modulating waveform is basically a function. It is either directly a state space variable or it is a function of the state space variable. And whenever it encounters at least an edge of the carrier waveform, a switching will happen. At that exact point, what will happen is that it will be a state switching will basically occur. And the interesting thing is that, okay, in case of the DC to DC converter, switching cycles are periodic orbits, and analyzing the stability of inverter becomes much more problematic. Why? Because the switching cycles are not periodic orbits. Why? Because there are two frequencies. You see, in DC to DC converter, there is only a single switching. Let us take it for the buck converter. This is the buck or boost converter. I mean, we are not basically dealing with, say, resonant converters. So what will happen is that in the DC to DC converter case, there is only one switching frequency, and when it is undergoing through a normal operation, see, when the state space either the inductor current or the capacitor voltage what will happen is that at the very initial stage, at the very beginning of the switching time period, you will just have to take a look at its value, and you will see during its normal course of operation, it will return to its that exact value at the end of the switching time period. But what will happen? See, just imagine the case of the DC buck converter, and imagine that upon it, a 50 hertz slowly moving waveform has been incorporated. So what will happen? Even during the case of normal operation, the state space variable, be it inductor current or capacitor voltage, will not return to that exact value from which it began at the very beginning of the switching cycle, switching time period. And that is the problem. That is the main problem while analyzing the stability of DC AC inverter. So what we do is we basically turn the entire inverter system into kind of a DC to DC system. We basically at all ignore the effect of the reference waveform of 50 or 60 hertz throughout the switching time period. And this is called quasi-static approximation. You see, small vref means basically it's the kind of AC quantity, and capital vref means it's basically kind of a DC quantity. So we will assume that at least throughout a particular switching time period, the effect of 50 hertz waveform, as I have said, it will inevitably turn the system into kind of a DC to DC converter. And what will happen is that in the case of a DC to DC converter, there is only a single fixed point. But the funny thing is that in case of an inverter, the number of fixed points will be the modulation index basically. If it is the switching frequency and if it is the fundamental frequency, and that much amount of fixed points will be there. Now, can you just understand the problem of analyzing stability of a system? Why two frequencies are there? Let us forget even about three frequencies. The problem is that do we necessarily have to, or I would say the question is that do we necessarily have to analyze the stability of 500 or the so and so, I mean, or 1000 or at least 100 number of fixed points? Or we can basically, in this case, just shift from the scientific side of ours into a more kind of an engineering domain, and we can basically say that, okay, in case of an inverter, we have particularly witnessed that all the fixed points will not lose stability at the same time. There is only one particular fixed point which will lose stability at the very initial onset of instability. And then all the other fixed points will gradually start to lose stability. For whose stability? The stability of period 1 waveform. Now, this is the same case. Remember that this will be the same case for the case of the PFC boost converter also. Where also there is like a two frequencies in addition to the switching frequency. There is a rectified frequency. I mean, it will be either 100 hertz or 120 hertz. So it is not like that inverter is kind of a standalone kind of I would say kind of an aberration. Inverter basically also dictates the dynamics of inverter, also dictates the phenomena for various other types of systems also, like PFC boost converter. Now, at this stage, let us ask a very fundamental question. We are going to delve deep into the idealized and parasitic modeling aspect. Because what basically happens is that, see, the very initial work on inverter began at 1997, and it was done basically a group of Carton and others. And since then, most works have avoided parasitics in their modeling. And even if you are opting for state space average approach, if you are just basically going to go for say Bode plot, okay, and if you just see whether the gain margin and phase margin are within the within the positive range, or is it becoming negative or things like that. Even in that case of modeling, you will inevitably opt for avoiding parasitics just to simplify the equation. And in doing so, you will avoid things like static drain source MOSFET switch on resistance or equivalent series resistance of capacitor or DC resistance of inductor. And the problem is that by doing so, what are you missing? That is the question. Because it has been seen from time to time that whenever there is some discrepancy between the analytical result and the experimental result, between the predicted result and the practical result, it has been, a common established practice, I would say, at this moment, till now, to blame it all upon this type of parasitic. And it is justified to some extent also. Why? You see, parasitics, if you just go through the, the technical documents, the data sheets of switches or inductors or capacitors, you will see that they have only provided a nominal value or a maximum value for a particular operating range, for a particular, I would say, for a particular temperature, or a particular operating temperature, particular ambient temperature, particular type of humidity, or things like that, particular type of, particular amount of voltage or current level. And what will happen during the course of the operation, when the circuit is in operation, those conditions are going to change. Then how can you quantitatively predict the effect of parasitic in basically shifting the result from the, say, ideal case to the practical case? Well, in a short answer, I would say you can't. Even if you can, the effort, I would say the squeeze is not worth the juice. You see, why should you undertake such an strenuous endeavor? You won't. But that does not mean that we should lose our scientific curiosity at this stage, and we should stop asking ourselves, what is the effect of each of these parasitics? Even those who basically doesn't at all bother, those of you who doesn't at all bother about this, this kind of bifurcation theory, chaos theory, you need not bother about it. But even in that case, you should ask yourself this question: how does each of these parasitic elements leave their mark in shifting the result from the ideal case to the practical case? And the effect is much more profound. In case of low power circuits, you can say that, okay, we can basically avoid the effect of ESRs of capacitors when the voltage level goes high, and you will be right to say so. Why? Because you will see that if you just go through the data sheet, you will see that when the values of the capacitors increase, its ESR basically decreases. And that's why, suppose in your system you have a, say, you have a 50 microfarad capacitor, or let us just say 47 microfarad capacitor. What will you do? Would you just say incorporate a direct 47 microfarad capacitor, or would you basically parallel 10 microfarad capacitors in parallel? I think you are going to go for the latter option, because especially see in the case of the electrolytic capacitors, the capacitors often tend to blow up. That thing is there. And not only that, when you basically connect the 10 microfarad capacitors in parallel, so you are basically also connecting their ESR or equivalent series resistance in parallel. So in effect, you are basically decreasing the equivalent resistance, which will be much lesser than that of the single 47 microfarad capacitor. But note the case that if you just take a single 10 microfarad capacitor, its ESR will always be larger than that of the 47 microfarad capacitor. But since you are paralleling 5 10 microfarad capacitors, you will see a much more reduced equivalent series resistance. And since no work has focused on this comparative aspect of modeling, as I was saying, with mathematical rigor and provide a definitive answer from an analytical viewpoint, I at least have undertaken this endeavor so that all of you need not go through the mathematical rigor, but all of you may get some critical answer. So let us just take a look at the schematic diagram of an idealized and parasitic modeling. See, on the left-hand side, you will see this is the idealized modeling without the switch turn-on resistance, DC series equivalent resistance of the inductor or ESR of the capacitor in this case. And in this case, you will see, as I was telling you, that this is a trailing edge type of modulation scheme sort of waveform. So when Vcon, the control voltage, which basically is the output of the proportional integral controller. Okay. So this is the overall controller schematic. So what happens when Vcon intersects VRAM? A switch occurs and mode A basically turns to mode B. And what does it mean? Basically switch S1 and S4 was on during mode A, when mode A was in operational phase. And when Vcon intersects VRAM at this stage, a state switch occurs, state switching basically occurs, state phenomena occurs, and mode A basically turns into mode B. And then see the switching time period begins from this point and up to this point, the switching time period is there. And at the end of the switching time period, there is basically this is kind of a discontinuity, but it basically suddenly just comes down. The rate of change of the waveform, the rate of change of the carrier waveform at this level is very high, near to 10, I would say near to infinity. And at this stage, another switch will occur, to which mode from the operational mode B, the overall system will then again will again be inserted into mode A operation. Okay, so at this stage, switch S1, S4 is on. At this stage, S1, S4 is off, and instead S2 and S3 is on. And then again, S2 and S3 turns off at the end of the switching time period. And this is called, as I was saying, a time event switching. This is a forced switching. Why it is called a time event switching? Because it will occur at exactly some particular time that has been impressed upon through this modulating type of through this carrier wave, external forcing function. Then you'd ask that what is the example of an autonomous system? The example of an autonomous system, for an example, if you just want to go to an example of the autonomous system, then I would say a DC-DC converter on an inverter operating in, I would say, hysteresis controller. You are familiarized with it, right? Hysteresis controller, bang controller. When that type of controller is there, you would see that there is no such thing such as external forcing function. There is no external forcing frequency, and the switching frequency basically tends to change with change in, say, load resistance values or input voltage values. Okay, and that's the problem with this type of controllers. It basically makes the design of filters very hard, even though very some time back, of course, you would say that okay, there is also the case of the fixed frequency autonomous or fixed frequency hysteresis type of controllers. But I would say it just makes the whole thing a little bit complicated, I would say. Now, if you just take a look at the various data sheets, you will see for the case of the N-channel MOSFET switches, which basically is kind of the IRF series, you see the IRF from 510 up to 540. What does it indicate? It indicates basically the operating maximum drain to source voltage is 100 volts. But when the second number basically starts to increase, say 10, 20, 30, 40, what happens is that the drain current, the maximum amount of drain current that can traverse through the switch during its on condition also starts to increase. And at the same time, when the current to the MOSFET switch starts to increase, you will see that the switch on resistance or drain to source resistance, switch on resistance also starts to decrease. Now let us take a look at the IRF 610 up to 640. This is the case for the 200 volt operating condition. And then again, from the 3.3 ampere up to 18 ampere, these things are basically, I think, available in the market still. And then the IRF 710 to IRF 740, these are for the operating voltage of 400 volts. And then for the 8 series, these are for the operating voltage of 500 volts. Now, there is, I mean, a large amount, I would say, huge amount of wisdom can be gained if we just fix our eyes on this table, which are basically compiled based on various data sheets. What can you see from here? Let us pose a problem. Let us pose a very practical problem. You see, in your system, you would need a switch, say, for 300 volts and 5 ampere. Then what is the type? What is the type of switch that you are going to go for? Say 300 volt and 5 ampere, then at the very first stage, you will go for either IRF 730 or IRF 740. The problem is that, is it available in the market? That is the big question. Or has it been gone out of production or unavailable in the market? Then what will you do? You will go for the IRF series. Then again, you will just have to go for what? This IRF 840. Then what will happen? See, in this case, say if you are going for IRF 740, the RDS switch on resistance was 0.55. And the switch on resistance has basically increased, right? And remember, always, in case of the inverter, two switches will be always on. So it will be multiple two. Interesting thing is that during your modeling aspect, you are completely going to disregard it. But what if it is a low power system? Then this thing might at least, I would say, even though, these things, especially in the case of the low power system, I would say, these things are going to pose a huge problem when you are going to tally your predicted result with that of the actual result. Similarly, you can see these are the two drain source on-state resistance of our gallium nitride transistors, which are now basically coming into place. Similarly, if you just take a look at it, you look at the inductor also. Nowadays, of course, some standard value inductors are also available in the market, even though their current rating is very low. And the thing is that after, I think I got about after 1 ampere or 2 ampere power chokes are also available in Chandni Chowk market in Calcutta. And the thing is that what will happen when you tend to disregard it all? Your scientific curiosity should force you to ask that question. I mean, an engineer is not just some kind of an technician. He should possess a detailed knowledge of mathematics also. That is what basically distinguishes the engineer from that of a technician. And you should have some scientific curiosity also. Let us have that curiosity. Let us ask ourselves that question now. And what will happen, say, for the case of the choke or inductor, as I was saying, when the number of turns increase, its resistance, DC resistance also goes up, right? In case of the capacitor, as I had already said, due to paucity of time or paucity of slides, I can't share you all the details, but it is in my thesis actually, which I can share you after a few months when it is entirely completed. And the thing is that in case of the capacitor, when its value increases, always remember that its ESR decreases. And this is the differential equations of the ideal system without parasitic for the inverter, of course. See, first two equations, this basically corresponds to the power stage, and this equation basically corresponds to the control stage. One thing that I have done in my work at least is that, you see, at the very outset, I was talking about the problem of analyzing stability of inverter. Why? Because there are two frequencies in it, and all the theories are developed for analyzing stability at one frequency only. That is why it is very much simple to analyze stability of a DC to DC converter, but it is not so. So when you are coming to a converter with two or even three frequencies, which is the case of the, I would say, AC to AC type of converter, you know. Or you can also say the type of DC system that basically connects in Japan, 50 hertz on one side of the island, there is a 50 hertz operating region, there is a 50 hertz operating region, and on another side, there is also 60 hertz operating region. And they basically have an HVDC station to interconnect those two frequency systems. And so basically this can be said as a typical example of a system with three frequency values. In that case, we will have to basically scale it down to kind of a DC to DC converter, right? That I was saying. And for that, the quasi-static approximation, that is the core to my work actually, you will have to resort to that approximation. But when we are analyzing stability of a system, what do we do? You can basically go to difference equation and form a map, or you are much more familiar with differential equation, even though solving a differential equation, I mean, it takes much more time, and of course, it's a little bit complicated. And at least for a lower order system, difference equation or map is a much simpler option. And in the state space representation, it basically comes to this, and don't be alarmed by the typical type of mathematics involved. But for theories, I would say, for just to give you some qualitative answer, okay, so by scientific curiosity, I had to resort to this type of equations and calculations. Now, just take a look at the differential equation of the ideal system without parasitic, and now take a look at the same system when the parasitic, resistive type of parasitic, I would say, switch turn on resistance, DC resistance of inductor, and ESR of capacitors have been incorporated. Can you just appreciate the difficulty that entails when we are going for the parasitic modeling, idealized modeling? That I think you can do at this very initial stage. And you can also see that in this case, there was only one type of equation which was different for both them. Now, in this case, when we are incorporating the parasitic element, you see that in case of the controller equation that is arising at the output of the proportional integral controller, actually, you will see that there are now two equations involved for the two, sorry, this is mode B positive, B prime, there is a mistake over here. So there are additional equation that is arising in the controller, which basically now has to be accounted for both them. The state space representation is in this case is basically the same to some extent, because the system basically is remaining third order system that we can see, and H1 X P and T, this is basically the switching condition. This is nothing but the algebraic equation where Vcon equal to Vram. Okay. Now let us just turn the equations with parasitic elements to a much understandable, to a much simpler, to a much simpler paradigm, I would say. This is what it would look like. And if we just want to make a comparison of them, this is how the state matrices and input matrices would look like. Now, when we are basically analyzing stability of a periodic orbit, what will happen is that the periodic orbit will basically go through the two linear subsystems. corresponding to mode A and mode B. Okay, which can basically be formed by the simple state transition matrices, with which I think you have basically read about it in probably third year of your undergraduate curriculum. Okay, but the problem that inherently arises is that when the periodic orbit has to go through a switching phenomenon, therein lies the problem. What we basically do, we basically give perturbation to the original solution, right? To the original periodic orbit and see how the perturbed trajectory evolves or how the perturbation in itself evolves. We basically try to see it, and we can basically see how the perturbation evolves to the linear time invariant subsystems when the switch is basically operating in either or mode, either in mode A or either in mode B, right? We can predict that evolution of perturbation through the simple state transition matrices. But there is a problem in predicting how the evolution of perturbation is through a switching phenomenon. For that, we need another type of state transition matrix. That is called haltation matrix. This is nothing but a type of a state transition matrix, I must say, which basically kind of takes into account the switching phenomenon. Otherwise, if we just multiply the state transition matrices and form a type of a Jacobian, then what it would do, it would basically be kind of an average system. It won't be able to predict, it won't be able to take into account the phenomena of switching. And the problem due to that is that in that case, it will not be able to predict. Suppose your switching frequency is 10 kilohertz, then in that case, it will not be able to predict anything beyond, say, 1 kilohertz. Anything happening within 1 kilohertz, it will be able to predict. I mean, there is not some explicit formula to predict it, but from our experience, we have seen that the average method or the type of Bode plots that you basically deal with, it can predict instability or dynamics of a system only up to 1/10 of the switching frequency or something like that. But as we if any instability that manifests at an higher frequency range, it won't be able to predict that. There is a thing called period doubling bifurcation or half scale instability, which basically happens at half of the switching frequency. For predicting that type of instability, you need to take into account some either discrete type of method or some, I would say, kind of a Filipov method that I have basically considered, or kind of a, I'd say, the trajectory sensitivity approach of Ian Hisken. Hisken's trajectory sensitivity approach, let me also tell you, that is widely employed in power systems. Why since 2008, the type of Filipov method has been widely employed in power electronics systems. Now, the haltation matrix for the third order system, this is the state transition matrix, which basically takes into account how the switching, how the perturbation evolves to the switching event. This is how it would look like for the state event switching. When mode A is basically going to mode B, right? This one. When mode A is going to mode B, you see, at that point there will be a switching. So when basically when the system is in mode A operations throughout this time switching time period, we basically constructed a state transition matrix for this period, and then another state transition matrix for this period, and then for this to switching, we need to take into account another 2 state transition matrices, which is called haltation matrices. At this stage, just take it as a fancy name, at least, okay? Just don't be too bothered by, just don't be focused on the terminology at this stage. But let me just tell you, this is a state event, as I had said. There will be a haltation matrix corresponding to this state event switching. And then at this point, there will be also a time event switching. And there will be a haltation matrix for this time event switching also. So now let us take a look at the state transition matrices for the two switching events. And this is how the faultation matrix for the state event switching will look like. Note that this is, we have termed as a generalized faultation matrix because there is a gamma term involved, which also basically involves the 50 Hz component within it. But how can we use it to analyze stability? Because no theory is there to analyze stability of an orbit which is not periodic. Let us answer it sometime later. And this is how the generalized faultation matrix that will look like for the case where the parasitic elements have been taken into consideration. See how much complicated it has already become. Just take a look at this two matrices. Now, what we will do is that to make these two matrices, state transition matrices or faultation matrix, suitable for analyzing stability, we will apply quasi-static approximation. Why? Because there is a gamma term or a 50 Hz frequency term or 60 Hz frequency term involved in it. What will happen is that we will either fixate it at the positive peak. Okay. Then it will come down to a case like that of the DC to DC converter case. Then it becomes, we can safely say, then when we try to multiply all the state transition matrices, 4 state transition matrices, then it will indicate stability of a periodic orbit. Then it will make some sense. Note that the first case of instability manifests in case of the inverter at the positive peak at 90 degrees phase angle. So that's why we are going to take that case of the fixed point as a typical case and leave rest of the 499 fixed point case. Because why? Because this is the frequency at which the period doubling bifurcation or period doubling type of instability will manifest for the first time. In case of the PFC boost converter, the first case of instability manifests at zero crossing, at 0 degree angle. Now, there are no theoretical proofs for it, but only based on experience, only based on observation, it has been fixed. So that's why we have basically going to fixate our case for this case only, for this phase angle only. For the state transition matrix for the time event switching, funnily enough, and at least which is a big respite to us, is nothing but an identity matrix. Because if you just take a look at the form of the faultation matrix, you will see there is a term called del H to del T, where H is the switching hypersurface or switching surface. Okay, now what del H del T means is basically the rate of change of switching surface. And what happens at the very moment of discontinuity at the end of the switching time period? What happens? See, what happens at this case? You will see that the del H del T, the rate of change of switching surface, is like tends to infinity, while T is basically tends to 0. Isn't it so? So that's what basically makes our case a little bit simpler when we are basically dealing with either the leading edge or trailing edge type of modulation scheme. The state transition matrix or faultation matrix for this case will be an identity matrix. Then we will basically multiply all the state transition matrices and then omit one, since S2 is basically an identity matrix, and the complete state transition matrix, cumulative state transition matrix, is called monodromy matrix. Its eigenvalues will now basically indicate whether the system is stable or unstable. Now, when you are basically dealing with state space average modeling, or when you are basically dealing with some linear paradigm of stability analysis, you basically try to keep the pole and zeros in the left hand side. You are basically analyzing the whole stability in the S plane, but in this case, it is basically in Z plane. So, when the eigenvalues are within the unit circle in the Z plane, then it indicates a stable system. And when even one eigenvalue is outside of the unit circle, then it would indicate an unstable system. Now, let us take some look at some analytical results. Okay. And for the first case, let us take a look at comparative analytical results on idealized and resistive parasitic models. At this stage, of course, let us try to answer this question. What are the qualitative and quantitative differences in analytical results? Qualitative term is more important from a scientific viewpoint, and quantitative term is more important, at least from a engineering viewpoint or technical viewpoint, I would say. Differences in analytical results between inverter systems with ideal modeling and practical modeling, with non-parasitic modeling and parasitic modeling. Can we just take a look at this table and see what you are seeing over here? See, when we are basically seeing the case for an idealized modeling, you will see that the Hop type of bifurcation or Hop type of instability or the slow time scale instability, which basically manifests at a much lower frequency, at least lower than 1/10 of the switching frequency, you see that the effect of incorporation of that parasitic elements is basically to delay the onset of the Hop type of instabilities. Right? Interesting, isn't it? You see, why wouldn't it be so? If you just think about it deeply. And basically, Professor Shen Sharma of IIT Kanpur, we were in a seminar last year at Trivandrum. I was also talking about it, and he was saying, okay, yes. You see, since we are from the power electronics, hardcore power electronics domain, we can basically appreciate this fact from another viewpoint. You see, what does this parasitic elements do, resistive parasitic elements do? These resistive elements basically, they impose the type of a resistive damping, right? And this in turn delays the onset of instability. And note that you can detect the Hop type of instability through a average modeling, right? So up to that point, you are familiar with, but at the very same time, it also causes a slightly earlier onset of period doubling instability, which basically happens at 1/2 of the switching time period. So remember that when it comes to science, you cannot predict something in absolute. You cannot predict that, okay, it will always cause some effect in unison. It will always cause delayed onset in every case. No, it will not be so. But from an engineering perspective, you can also say that the onset of period doubling instability will be basically more or less at the same level, but never be at a delayed level. And you can only predict the onset of period doubling instability through Filipov method or discrete time approaches. You can't predict it by state space modeling approach or Bode plot. Let us just appreciate this fact in a parameter space. On the left hand side, there is the controller parameter space. Kp is the proportional gain. TO2 is basically, TO tau is basically a kind of a, you can say, to a constant term. It has been elevated, but this basically refers to the integral gain constant or integral time constant, I should say. And then on the right hand side, there is the VNR parameter space. What can you see over here? You see the dotted line indicates the line through which Hop bifurcation or slow scale instability occurs. And you can predict this line, these two dotted lines, by using your simple linear approaches. But you can't predict this solid line through which, I mean, if you, when the system traverses through that solid line, period doubling instability occurs. And you can't predict it through using the simple state space modeling approach or average modeling. And what can you see? Can you see that the onset of instability, fast scale instability or period doubling instability, more or less basically remains at the same level, but can you also see that due to incorporation of the parasitic element, the onset of instability has been delayed to a great extent because the red line indicates the parasitic line, stability boundary obtained through the parasitic modeling. And that is the interesting case because in your case, what is your aim? Your aim is to ensure stability of your system. That is the simple thing. That is your simple objective, right? And now, through this analytical approach that I have left some rigorous mathematical parts, of course, in this presentation. I can now give you some answer. When your objective is to ensure stability of your system, just go for the simple, idealized, non-parasitic modeling. There is no need to go for the much complicated parasitic modeling. Why? Because in either case, your system will be within the stable zone. It might be a little bit damp system. We can deal with that, right? At least your system will be stable. But if you want something kind of an accurate result, then of course you will have to go for the parasitic modeling. But can you appreciate now how the parasitic elements have an effect on the stability boundary, especially if it is a, I would say, low power circuit? How much can you see over here? It can elongate the stability zone. That is something to think about, right? These things are called bifurcation diagrams. At least those who have dealt with bifurcation theory, chaos theory are very much familiar with it. But for those who are unaware with it, let me just give you an simple elementary 1 minute tutorial. You see, when there is a single line, that indicates the stable zone. And anything other than that simple single line, it indicates unstable zone over here. Now, when there are two lines instead of single line at a particular parameter, it indicates period doubling bifurcation, where basically the same state repeats after 2 clock cycles, right? This frequency of if your system switching frequency is say 20 kilohertz, then at this stage the system, this instability will manifest at 10 kilohertz. That is why there is two lines. And in this case, the stability is lost to Hopf bifurcation. Note that you can predict this type of instability through Bode plot or linear type of any analysis. But for predicting this type of instability, you need some type of discrete time approach or Philippon method, or the other method. Then, can you appreciate the fact how, due to incorporation of the parasitic element, the onset of instability is elongated, is delayed in the lower case, but for the case of the period doubling bifurcation, you can say that you can safely say that this the onset of it is more or less similar. These are the bifurcation diagrams for the power circuit parameters. Now, to summarize, for the first case, based on the rigorous analysis that I had undertaken but has refrained to show you some over here, the answers to our questions is that qualitative results remain similar. Why? Because the same type of instability will manifest due to incorporation of parasitic elements in the modeling. No such new type of instability. I mean, if there was a Hopf bifurcation, it is not like that the parasitic elements will cause a period doubling bifurcation in that case. But quantitative disagreements will be there. That I have already shown you. And quantitative disagreements is more profound, is more prominent for the case where there is Hopf bifurcation. However, quantitative results are almost similar to the onset of period doubling bifurcation. And since ideal model predicts slightly earlier onset of period doubling bifurcation, we can make this recommendation. When the objectivity of stability of period 1 orbit, it is recommended to opt for idealized modeling because it is much more simpler. Okay. Now, there is also another thing. See, when you are constructing the inductor by your own hand, what will you do is that you wound the wire around a core, but suppose our nominal value is 220 microhenry. It will be hardly the fact. Even if you just suppose you are dealing with an E type of core, and then of course you can basically play with the air gap. You can insert some kind of a paper or dielectric or insulating type of material. Okay, and then you can basically play with the air gap of the inductor and basically try to make the value of the, in case of the experimental case, as much as close to the nominal value, which you have used for the analytical case. But it would hardly be the case where it is exactly same. In that case, also, we need to see how, for at least in this case, we have given it a 10% of variation around the nominal value. In that case, we will have to see how much the onset of instability shifts, right? And what can we see? For higher value of inductor value, you see the onset of period doubling instability is delayed. And the onset of period doubling instability is also delayed. Thus, we can make an uniform statement over here. But for the case of 10% swing around the nominal capacitor value of say 20 microfarad, what are we seeing? We are seeing that an earlier onset of type of instability, but a delayed onset of period doubling instability. Now, do you have an appreciation of the fact why your actual practical result often differs so much from your predicted or analytical result? And I mean, the practice is just to say, okay, there is some, the hand waving type of statement. Okay, there is some due to some I'd say parasitical event, due to some type of non-idealities, this type of disagreements are occurring. But we have to keep in mind that as engineers, we also belong to the scientific domain. Are we allowed to say that type of hand-waving statement? No, we can't. We must at least possess some qualitative idea on how, due to each of the small and ignored factors, you see, we tend to ignore this type of factors, but how do they influence the overall fundamental and actual outcome in the long run? You must have some appreciation of the contribution of each individual factor. And the interesting thing about is that often these factors will counteract each other and then bring the final result, final practical result, somewhat closer. They may bring it. They may, I would say. I re-emphasize on the term of may. They may bring the final result somewhat closer to the actual predicted result. This is much more. Okay, in this case also, we have taken the case of the IIEST, and the results are more or less, I would say, similar. Okay. And in this case, now, we have so far left out the case of the inherent time delay. And again, I say that often this type of non-idealities that we tend to ignore in our modeling process just to make it a simplified process. And as an engineer, you are justified in your simplified approach. But you will often see the results disagree to a great extent, but you will also see the results often agree. Why? Because you will see that often this type of parasitic elements counteract with each other. And when we take the case of the inherent time delay, which basically arises now, this is arising in the controller circuit. This is not arising in the power circuit. Note that till now, all the parasitic elements, resistive parasitic elements, basically and also some variations around the nominal inductor and capacitor, filter capacitor and inductor values. They are all arising out of the power circuitry. Now, what about the inherent time delay and how does it manifest? That is the first question. If you just go through the data sheets of various IC chips or the transducers or sensors, you will always see some kind of delay time, response time, rise time, this type of, I'd say, quantifications are mentioned. And when it comes to, the type of time delay is much more pronounced, I'd say much more important in the case of the digital circuitry, of course. But let us take up the case of the analog controller, at least. Yes. Yes, is there any question? Okay, if there is not, then let me just proceed to it. The thing is that when it comes to a simple controller, a simple voltage mode controller, or even a simple current mode controller for a buck or boost converter, it is highly unlikely that you are going to opt for the digital circuit, digital domain. It is much more likely that you are going to opt for the analog domain. And the thing is that in the analog, when you basically try to construct an analog circuit, what you will do is that you will just basically stack this type of IC chip on a single breadboard for the initial case, and later you will just implement it in a much more, I'd say, sophisticated way, of course. But this type of time delay will be manifested for each of the IC chips that you are going to use in your controller. And together in a unified fashion, I would say, all of it are going to basically contribute to the cumulative time delay. But how can we model it? Note that time delay basically is kind of an infinite dimensional system. If you just take the case of the e to the power minus tau d, okay, this is an infinite time dimension. But we can take the case when we basically just sum it up at some point. And where are we going to sum it up? Just at the input of the comparator. Why? Because you see, the comparator is a very interesting thing. At the input of the comparator, you see that it is basically a kind of an continuous analog domain. But at the output of the comparator, it is like a digital domain, right? It will provide either high or low signal. It will either provide 1 or 0, yes or no, right? So we are going to incorporate our inherent time delay module, which is nothing but e to the power minus tau d, to account for how the inherent time delay that is arising out of each of the IC integrated circuit chips at this point. Okay, and then see how does the inherent time delay affect the stability analysis of the system. So, at this stage, let us ask a question. What is the type of delay-induced instability and critical time delay threshold beyond which instability sets in? That is the first question. And how does the inherent time delay affect the stability boundary in control and power circuit parameter spaces, even if it is within the critical delay threshold? The last portion of the question is very important, because in all practical cases, you will see that your analog controller will, the cumulative time delay of your analog controller will never exceed the case where it is readily bringing in some type of instability. you will see that it is always within the critical delay threshold. But that doesn't mean that it won't leave its mark. This is how the differential equation of the ideal system without time delay module could look like. Note that this is a third order system. And we will basically make a Pare approximation of the inherent time delay module of the infinite dimensional time delay module into a single dimensional module. This is an approximation that this approximation can be readily be found in the book of K. Ogata, where our overall dimension of the system will increase only by only one. Okay, but it should be noted at this point that the system will exhibit non-minimum phase behavior due to the right-hand side zero in A state. Can you see that there is a right-hand side zero over here? So at this very stage, initial stage, you can say, okay, since it is incorporating a right-hand side zero, it will incorporate some type of instability at this stage. Okay. Now we need to convert the S domain equation into continuous time domain and then form our differential equation. So in totality, it would be like a fourth order system where the differential equation due to the time delay module would be manifested as such. It would be much more beneficial for all the listeners if you just mute your microphone, right? Otherwise, this type of ambient noise is causing a nuisance. Okay. Let us now go to how the state space matrices and vectors due to the integrated time delay module would look like. You can readily see that due to incorporation of the time delay module, the overall dimension has already increased by an order, but that is more than enough for us to predict the qualitative effect, and from both qualitative and quantitative perspectives, the effects are due to it. Right? This has already been discussed. This is the form of the state event switching. And this is the sortation matrix for the state event switching when we have basically considered the time delay into account, right? And note that in this case also, there is two additional state variables. And in this case also, you know, the state transition matrix for the time event switching will always be an identity matrix for the previous case. For all the case, whenever we are dealing with a leading edge or trailing edge type of modulation scheme also. And this is the thing is that to answer the first question, what we are seeing for the nominal type of parameter values that we have taken into account, we are seeing that at less than the 10% mark, actually, 10% of the switching time period, I think for our case it was like 25 kilohertz, so 40 microseconds was the switching time period. And even at lesser than the 10% mark of the switching time period, manifestation of instability was occurring, and this was occurring to the Hop bifurcation. And the interesting thing is that you can predict it to state space average modeling or Bode plot. So to answer the first question, what is the type of delay induced instability and critical delay threshold beyond which instability sets in? It is basically a Hop bifurcation induced instability. And if we just take a look at the table, we can clearly see that whenever it comes to an Hop bifurcation, onset of Hop bifurcation, can you see that the Hop bifurcation, the critical parameter value at which Hop bifurcation is occurring at a much earlier stage. Interesting, isn't it? But what about period doubling bifurcation? You can also see that even in some cases, the period doubling bifurcation is not only occurring also to a meagerly earlier stage, but in some cases it is often being replaced by the dominant Hop bifurcation. So can we say that the inherent time delay that is arising out of the integrated circuit chip is a Hopf bifurcation inducing phenomena? That is the question. And if we just take a look at the parameter space, the stability boundary in the parameter spaces, we can clearly see how, due to Hopf bifurcation, due to inherent time delay, the stable zone is diminished. You see the black case is for the ideal case and the pink case is for the case where inherent time delay is there. So to answer the next question, how does the inherent time delay affect the stability boundaries in parameter spaces? Even if it is within the critical delay threshold, which would be the normal case, okay, which would be the, because in many cases, many people have asked me, whenever we are dealing with analog controller, okay, in case of the digital type of controller, I mean, this problem is there. The problem for instability is there. But when it comes to the analog controller, we have never seen the effect of inherent time delay. That is because in a normal case, yes, the system remains within the critical delay threshold and will not readily exhibit some type of instability. But that does not mean it will diminish the stable zone. As you can see over here, right? In this case, you see we have taken it as the inherent time delay as 2 microseconds. This is for 0 microseconds. And the instability was occurring at 3.36 microseconds. So it is perfectly well within the critical delay threshold, but that does not mean that it hasn't left its mark. Now, can you see the interesting case of it? The thing is that the unwanted effect, the unwanted inherent time delay that is arising out of the controller circuitry is basically kind of the opposite phenomena that is occurring in the power circuitry, that is arising in the power circuitry due to the resistive parasitic, where the stable zones were basically elongated or enlarged. But in this case, the stable boundaries, stable zones are uniformly diminished. That's why I had said earlier that in the practical case, you may often see that due to counteracting nature of these two type of phenomena arising out in the power circuit and in the controller circuit, they will basically counteract each other. They will basically act kind of an opposing type of behavior. And I again emphasize on the term may cause your actual predicted result through your analytical procedure, whatever it is, somewhat similar to that of the ideal system behavior. But if it is not so, then I think as an engineer, as a scientist, as someone who belongs to the domain of science, applied science, it is our duty and responsibility to know how each of these factors contribute to this aspect. This is some type of effect of the inherent time delay. But you can readily see this is the type of chaotic type of behavior at 4 microseconds that has manifested for it, and due to manifestation of the chaotic type of behavior, the THT has also increased, I mean, beyond bounds. That is the term I would prefer. And in a comparative aspect, if we just try to take a look at it, you can see the black case is for the ideal case, the pink case is for the case where 2 microsecond inherent time delay is there. And you can clearly see that the onset of instability is occurring at a much earlier stage. Why? Because the straight line, simple straight line indicates the parameter value for which stable period 1 behavior is there. And you can clearly see the pink zone is basically transitioning from the simple straight line to this type of unwanted dense zone, I would say, at a much earlier value of the parameter space. But for the case of the onset of period doubling bifurcation, you can clearly see that it is more or less, I would say, similar. But in that case also, from period 2 to chaotic behavior is also occurring at a much earlier stages. So we can make a recommendation at this stage based on the rigorous analysis again that I have done on your behalf on the scientific communities that we have done. That is, I mean, as each of our individual responsibility, of course. So the thing is that as inherent time delay has profound effect on hop bifurcation while having minimal effect on the onset of periodic doubling bifurcation, you can basically opt for the simple average method-based analytical approach or the Bode plot-based approach, whatever linear paradigm-based approach with which you are comfortable and familiar with for performing this type of stability analysis. When you are basically dealing with inherent time delay. Now let us take the case of the proportional resonance controller. Why? Because we see when it comes to the proportional resonance controller, it has basically manifested, I think it basically manifested for an active power filter or something like that, and by Japanese group. And if you have just have some qualitative idea about the internal model principle, and what does the internal model principle say? It says that whatever disturbance that has to be rejected or a model of the plant has to be incorporated within the controller structure, right? In a layman's term, I think this would be something like the definition of it in a layman's term, of course. And what happens is that the proportional integral controller basically introduces a infinite gain at the 0 hertz, and it is much more ideal for the DC to DC converter. Why? Because in case of the DC to DC converter, our objective is to eliminate the steady state error at 0 hertz at the DC component, right? So for the PI controller, is very much apt for the DC to DC controller. But when it comes to the inverter, where our objective is to eliminate steady state error at the 50 hertz for the 50 hertz component, right? At the 50 hertz frequency, then we have to incorporate something like a resonance term which would induce an infinite gain at that particular frequency at 50 hertz or 60 hertz frequency. But the thing is that all the analytical paradigms are basically focused upon the case of the PI controller, even in case of the inverter also, and even in case of the PR controller, some rigorous analytical results are still missing. So let us just say at this moment, if the dynamical behavior of the proportional resonant controller is somewhat similar to that of the PI controller, and what is the importance of this question? Because if it is similar, then we need not go into the details of the stability analysis of this type of controller, right? Because the large volume literature is already there for the case of the PI controller, actually. So we'll just have to see whether the behavior is similar or dissimilar. This is the type of schematic diagram. And this is the fourth order state space representation. Why? Because in case of the PI controller, of course, there was in case the power circuit was basically incorporating 2 state variables and the controller circuit 1 state variables, but in case of the PR controller, the controller circuit is incorporating 2 state variables. As you can see, there are 2 poles over here. These are the basic state and input matrices. We can also express the state space representation in terms of the vector fields, which is nothing but another representation of the differential equation. And this is how the faultation matrix for the state event switching would look like. Much simpler, isn't it? And the X4 term is only arising at the output or due to the output of the proportional resonant controller. This is how the state space variables have been assigned, VPR and DVPR DT. And this is a more, I'd say, detailed schematic where we will again see the comparative aspect and again ask ourselves the same question: what are the qualitative and quantitative influence of the parasitic elements upon the dynamics of the inverter with PR control? Does it bear any resemblance? Does it bear any resemblance to the case for the inverter with PI controller? That is our question. And this is the faultation matrix for the case the inverter with parasitic elements. We can see in the numerator in this case, there is some added complexities, of course, but the state space variable remains similar. There is the X code. And let us just take a look at the bifurcation diagram for simplicity at this stage. What are we seeing? Is that in this case, due to incorporation of the parasitic elements, of course, there is a delayed onset of hop bifurcation also in case of the PR controller. But when there is comes to the onset of period doubling instability, we can also see not only that it is occurring at the same scale, nearly at the same value, but for the lower values, we can also see a new zone where hop bifurcation basically manifests. But in this case also, the effect of the incorporated parasitic is to drive away the hop bifurcation and diminish the zone where hop bifurcation basically occurs. Similarly, we can also witness the same case for the case of the when we are considering the resistive power circuit parameters also, we can also see that there is a delayed onset of hop type of instability. Now, to make something simplified for the community, so what we have done is that we have plotted the stability boundaries in the parameter spaces by applying Filipov method. So what are we seeing? Just as the previous case, we are seeing that the onset of instability, this is the zone where period doubling instability occurs. We can clearly see that the effect of incorporation of the parasitic elements is to increase the zone where hop bifurcation occurs. But at the same time, period doubling is also occurring at an earlier stage, right? And can you see that this discrepancy is much more pronounced than the case of the PI controller, but the qualitative behavior more or less is same. And in this case also, for the ideal case parasitics, there is a zone beneath which instability occurs and beyond which instability occurs. But when parasitic elements are incorporated, it basically drives away the zone, this zone of instability, and basically it stabilizes the whole zone as the stable zone. At this stage, of course, we can clearly say that while the qualitative behaviors are more or less similar, you see the quantitative behaviors, of course, when it comes to the quantitative behaviors, there are some minute differences, of course, than the case of the proportional integral controller, other than the case where hop bifurcation manifested for this zone, other than this zone. Now let us take some direction towards some chaos controller, and of course from notch filter based controller to unified resonant notch chaos controller. That is our first next objective. And the thing is that so far the efforts on chaos control have always been dictated by basically mathematicians and scientists, that they have only taken that kind of system, say one-dimensional math, which is nothing but a current mode controlled inverter, which is, I would say, a highly impractical system. They have always taken that type of system for their investigation. Why? Because investigating a single dimensional map is much simpler. Of course, when investigating stability of a lower order system is much more mathematically simpler. And what happens is that the time delay feedback control, that is the type of chaos control that was manifested. I won't go into the details of it. What happened is that the practical implementation of it is very much difficult. And so it was implemented by a notch filter in a PFC AC to DC boost converter. So why this notch filter? Why this type of chaos controller? That is the question you must be wondering at this stage. You must be even lost at this stage. Let me tell you why. Can you see when the period doubling bifurcation occurs, what happens? Suppose at this stage, the only dominant frequency was 20 kilohertz, say the switching frequency. But at this stage, in addition to the 20 kilohertz, 10 kilohertz frequency also comes into place, right? and we'll have to eliminate that frequency component. How can we eliminate that 10 kilohertz frequency component? By incorporating an infinite attenuation at the frequency component. How can we incorporate that infinite attenuation at a particular frequency component? Through a notch filter, right? That's what they had actually done. But so far, they have somewhat left the voltage mode control systems actually. Why? Because it is very much tough to analyze a voltage mode control system. Leave alone, I mean, even the case of the inverter, it is even much more tough. It is even tough. I would say it is even a tough job to analyze stability of a voltage mode control buck converter, because the equations are never comes in closed form. They are always in transcendental form, and when they are not in closed form, at least it makes the job of a mathematician much harder. So what we did was incorporate a notch filter in series with PI control, and then we saw incorporation of that controller, the notch type of filter, to drive away the period doubling frequency component, how much it was effective. We can clearly say not only it was effective in eliminating the period doubling route to chaos. Can you clearly see it? The scales are of course in different scale, unfortunately. But in this case, when notch filter is there, the instability is occurring at say around 70. I can say 65 to 70 for the value of Kp. Whereas without that notch filter, it was occurring at say beyond slightly 7.5 value. Whereas in this case, it also delays the onset of Hop bifurcation. So there is an immense importance in incorporating notch filter based compensator when we are basically trying to drive away instabilities to a much lower later stage. These are basically the power circuit parameters, where the same thing has also been seen, where the instabilities are occurring at a much lower stage, and the period doubling zone to chaos has been basically eliminated and replaced by a type of a Hop bifurcation, which is needless to say occurring at a much later stage. And to just show you how much difficulty entails in analyzing this type of system, is that now we are considering a sixth order system, right? This much you can see, and this is the transfer function of the notch filter. So can you see how much difficult it gets? But of course, it is very much effective, even in case of the proportional resonant controller, in not only eliminating, and this is not the period doubling bifurcation to chaos, note that. This is the Hop bifurcation, this is kind of a Hop bifurcation that is manifesting at much lower stage. And in the case of the proportional resonant controller also, we can see the effectiveness with which the notch filter with this transfer function. Okay, omega SW is half of the switching frequency to drive away the period doubling route to chaos. You can clearly appreciate how much effective it is in delaying the onset of instability. Now, from that, we can take an inspiration to derive an unified resonant notch chaos controller. Why? Because you see, the proportional resonant controller was derived through a simple application of the internal model principle. Then, in turn, we can also say in a way that the basic fundamental theory of notch filter in delaying the onset of instability also derives from the internal model principle, right? So we will just try to combine the case of the notch filter and proportional resonant controller into a single transfer function, if we can do so. That is our objective over here. And more importantly, we are going to follow a simple linear transfer function paradigm based derivation. We are going to follow the path of the, the Bode plots, with which almost all engineers are well acquainted, right? let us now just, you are basically familiar with this type of block diagrams of the inverter, right? This is the transfer function of the power stage of the inverter. Note that in case of the DC-DC buck converter, this two term will not be there. This two factor will not be there. This is the frequency response plot of the linearized power stage. And of course, the pulse width modulator gain is nothing but kind of an attenuation factor. And then combining the feedback gain and the open loop transfer function can be formulated as such. This is a very simple and straightforward approach. Then let us define our objective in a mathematical way, right? Don't be alarmed by the mathematics of it. Our basic objective is, the first objective tells us to incorporate an infinite frequency at the 50 Hz component. The second objective tells us to incorporate an infinite attenuation at half of the switching frequency. The third objective tells us not to have net positive gain at 0 Hz. There is no point in giving a positive gain for the case of the inverter at 0 Hz. We want to eliminate the DC component. We do not want any DC component within the inverter frequency component, right? And in the book of K Ogata, these two conditions are there. The gain margin should be greater than 6 decibel at least, and the phase margin should be less than 6 degree to greater than 30 degree for optimum and quick response, so that the system does not get much overdamped. And if we just go through the simple theory that has been espoused in the undergraduate textbook of Katsuhiko Ogata, we can clearly see that this type of factor, quadratic factor, will introduce infinite gain, and we can tune it to provide infinite gain at 50 Hz, right? Then, even though practically implementing this factor alone is an impossible task, this is not I mean the ideal form, right? So this will, let us just take a look at it mathematically. This will we will see an infinite attenuation due to this factor at the term of the half of the switching frequency. Okay. Now let us try to combine these two factors with 2 poles and 2 zeros, and let's see where we are getting. This is a simple intuition-based derivation, right? We are arriving at this stage. This is the Bode plot of that transfer function in alone. But what about the Bode plot of the combined system? And we can clearly see that it is still failing to meet the third criterion, the DC rejection criterion. So let us just proceed a little bit further. Let us just introduce an additional attenuation term, okay, the KU term, to solve the problem of negative gain margin. And we can also be small value of zeta, so it would increase the resonant peak at 50 Hz. You know that. Let us just put at KU at 8000 at it as 0.001, and then we can clearly see we are getting somewhere. And still, whenever, even though we have obtained the positive phase margin, gain margin, we are still getting the negative phase margin, and to compensate for the negative phase margin, we may incorporate a first order lead compensator. Okay, this will of course incorporate an additional degree with the system, but finally we have arrived at the Bode plot, at the frequency response plot, about which we had basically dreamed about at the very outset. But in totality, this is basically manifests as a fifth order system. But we basically wanted to make something, you see, which would mimic the combined behavior of proportional resonance controller with notch filter. So can you see that when within a reduced order, we have basically arrived at the same type of, I would say, we have basically to somewhat extent been able to meet the same type of objective. And this is how the saltation matrix would look like. And we can also basically implement this type of unified controller that we have used the term for it, for the DC-to-DC buck converter also. And this work was recently presented at a conference at Imperial College London, where I was physically there. And I would say that it has been well received, at least at a conceptual stage, it has been well received at a global stage. This is basically nothing but the similar thing for the DC-to-DC buck converter. Now, compared to sixth order inverter with PI controller and notch filter, fifth order inverter system with the proposed unified resonant notch chaos controller would achieve both of the primary objectives. And the same linear paradigm-based conceptualization can be extended to a buck converter as well to devise an unified double integral notch controller. And overall order of the system would be 5, same as a buck converter with PI controller and notch filter. Whatever is for the buck converter with PI controller and notch filter, it is the same thing from dynamics point of view for the inverter with PR controller and notch filter. Always remember that. For the buck, it is PI. For the inverter, it is PR. Finally, it is the final stage we have done. So far, we have only considered the linear load, but at this stage, our curiosity propels us to take the case of the non-linear rectifier load. So let us just take a look at it to some extent. See, this is the basic on the right hand side, upper right hand side. This is the basic, I would say, non-linear diode rectifier bridge load, and these would basically incorporate a very weak type of non-linearity at 50 Hz, because diodes are basically switching at 50 Hz, not switching frequency. And in the switching frequency based modeling for stability analysis, note that this diode would basically be left out. The switching phenomena would also be left out, but that doesn't mean that the non-linearity of it needs to be disregarded at all, because there is an additional capacitor at the output of it. We need to always remember that. And these would basically contribute a type of weak non-linearity at 50 Hz, not at the switching frequency. So, again, let us begin our last phase of my talk by asking some questions. Because as an engineer, not only as an engineer, but as a scientist, we should always ask ourselves some questions and should try to answer them. So what are the differences in qualitative and quantitative behavior between the linearized and nonlinear switch modeling of the rectifier? Isn't it the most obvious question at this stage? Why should we go for the nonlinear model? Does it offer any additional insight and information? If not, then we need not go for it. Isn't it so? And what we intend to do is what we basically do most often do is that we basically linearize the whole nonlinear load based on first harmonic approximation, and basically take a kind of linearized load in case of that highly, I'd say, highly nonlinear load. Then the next question is, whether all these pictures, as you have seen, are from our campus at IIEST Shibpur, which is basically one of the oldest engineering institutes. And before even this institute came into being, it was known as Bishop's College, where the giants and giants of Bengal Renaissance were basically present. And this has played a great role, I'd say a very prominent role, for at least the past, more than past 150 years, for the upliftment and for the intellectual development of the Bengali population. And our next question is, now let us come back to the case of the next question. So when compared to a linear resistive load, does the nonlinear rectifier load with equivalent load resistance uniformly diminish the stable zone of the system in control and power circuit parameter spaces? And this question is very important, because we always try to think, just like the case of the the parasitic case, we always think of this nonlinear type of thing as some kind of a very bad thing. it will always some kind of aggregate stability status. It will always some kind of a diminish the stable zone in parameter space. We always tend to see in a negative sense, but we must free ourselves from any kind of judgment. That is the most important lesson that we are going to learn as an scientist. If we want to become some kind of scientist or engineer, we must get ourselves rid of these preconceived notions and any judgment, any judgmental notion. Also, what is the effect of the rectifier side filter capacitor? Because we often tend to ignore it. This is a very detailed table, but this basically shows what is the type of instability that manifests. Okay, and these eigenvalues has already been computed by application of the Filipov method. Again, the details will not be shown over here, but let me show you something which can be readily be appreciated. And we can clearly see over here is that, you see, stability boundaries in control circuit parameter spaces and power circuit parameter spaces. And can you see this blue line? This blue line has been obtained by state space average method. Okay. This is the type of stability boundary that you are going to get when you are opting for a linearized approach. But note that it will also going to indicate this unstable zone where period doubling bifurcation occurs as unstable zone. That is the main problem with it that I have already repeatedly shown. And this is how the bifurcation diagram, this is how the instability will manifest. This is the onset of bifurcation. This is the onset of direct, chaos to border collision, a type of kind of a catastrophic type of bifurcation. This is the onset of period doubling bifurcation, right? But the most important case in this case is that what would happen if we just linearize it, linearize the nonlinear load? How much the results could differ then? This table basically answers that question. We can clearly see that in case of the nonlinear load model, the onset of instability when it comes to Hop bifurcation is much earlier. That goes with our preconceived notion that, okay, this is kind of an unwanted phenomena. But when it comes to the period doubling bifurcation, note that you can't predict this type of instability with your Bode plot or state space average based approach. Then what we are seeing a type of a delayed instability. That's why I had told you that always get rid of any preconceived notion when it comes to science. And when surprising things might often turn up. Let us just see it in a stability boundary domain. You can see that the red trace has been plotted for the nonlinear load and the black has been plotted for the linearized load, and both have been plotted by application of the Filipov method. Okay, it has not been plotted by any averaged linear method. What are we seeing? We are seeing that in case of the nonlinear model also, that the same thing that we had seen in the table, it is basically causing earlier onset of Hop bifurcation but delayed onset of period doubling bifurcation. Isn't it interesting? Now let us put the bifurcation diagram. We can see the same thing. See, the green trace is for the linearized trace, the linearized case, and the black trace is for the nonlinear case. So the nonlinear case for the nonlinear load modeling is causing earlier onset of instability, but at the same time, the nonlinear load modeling is also causing delayed onset of period doubling instability. This can be seen over here also for the power circuit parameter spaces. Earlier onset of instability for the nonlinear model, but delayed onset of instability when the instability is period doubling bifurcation. So let us conclude in comparison to the linearized rectifier load based on first harmonic approximation constituting a third order model. Why we basically tend to linearize it? By linearizing it, we basically tend to disregard the rectifier side capacitor and make it a third order system, right? We basically take kind of a, you'd say, kind of a first harmonic approximation. We basically take an equivalent load, something like this, based on first harmonic approximation. Okay. Then what happens is that we can appreciate now the fact that drastic quantitative differences are there, even if it is not like qualitative difference. Like it is not like that some new phenomena has been discovered. The same phenomena has been discovered, so same phenomena have been witnessed. But it is not that in the case of the nonlinear load modeling, one phenomenon is occurring at an earlier stage and one phenomenon is occurring at a later stage. This is some kind of interesting thing about this. And this paper was published in International Journal of Circuit Theory and Application. And we can interpret this result as the rectifier load when compared to an equivalent resistive load does not uniformly aggravate stability of the system. And let me just conclude at this stage. So I have basically tried to give you some qualitative and scientific ideas, which will basically help in your endeavor in becoming a better engineer or better technician. Because I have always believed that we must ask ourselves some fundamental questions. We never deviate from this path of asking ourselves some fundamental questions. Okay, and then we might see that we might get some surprising results. That is what basically I would say the interesting aspect of doing this work. So thank you very much for your patience in listening to this long talk. I hope I have been able to contribute at least some knowledge in this August gathering organized by Dr. Arnab Ghosh of NIT Rourkela. And thank you very much.
Am I audible to Aranya, sir? Am I audible to Aranya, sir?
Thank you, sir, for your wonderful presentation on small signal applications, small signal stability analysis, and nonlinear dynamics. Hello.